Now for the main event. Our speaker tonight is David Miller. David is a graduate student at Stanford, an undergraduate student at the University of Chicago, where he worked on a small particle physics experiment. He came to Stanford to work on a giant particle physics experiment. As you'll see, he is now a member of a worldwide collaboration at an accelerator based in Geneva, Switzerland, 3,000 physicists from all over the world. It is very daunting for a graduate student to make an impression in such a large group. To do that, you have to be incredibly brilliant, work 24 hours a day, and stick your nose in everything. And that's what David is known for. We managed to pry him away from his computer to come and give you a talk about what is going on now at the LHC. So without further ado, let's smash some protons. Thank you very much, David.
All right, so I hope everybody can hear me. I'm often actually told to be even more quiet than usual, so let me know if you can't hear anything. It's really an honor and a pleasure to be here tonight. I'm going to try to describe to you and lead you through a little bit of a story of what we do at the Large Hadron Collider. As Michael introduced, this is an extremely large worldwide collaboration, but one in which SLAC plays an integral role. We have a large group of physicists and scientists that are both there and here working together with people from all over the world to understand what's going on in this really unique accelerator, this really unique machine. So without further ado, let's actually get started. So I'd like to put this whole picture in a little bit of a context by showing you a short video where we take you from the outer reaches of the cosmos down into Geneva, Switzerland, where the experiment's actually taking place. So you're all familiar with the Milky Way, where we actually sit. And in fact, the accelerator is located just outside of downtown Geneva. So as you zoom into Europe and Switzerland, and now into the city of Geneva itself, you can see the outline of the accelerator sitting on the surface just outside of downtown, which is over here. But in fact, the accelerator itself sits almost 300 feet underground. So taking you there now, this machine is very unique. It's 17 miles around. It's located 300 feet underground, and each of these experimental halls is actually the site of the proton-proton collisions that are hopefully going to help us understand the basic fabric of the universe. And so these are the locations that we perform our experiments on a daily basis. Millions of proton collisions occur every second. And in fact, as we dip down into the accelerator itself, you can see the magnets which bend these around this huge arc and actually eventually collide at the location of the various experiments, which then take snapshots of what happens in these enormously energetic collisions millions of times a second. So I'd actually like to just briefly show you one more short video where I point out the actual collisions themselves. So the protons start in a booster system on the edge of the accelerator, and then they're shoved into a small ring where they get up to speed, nearly the speed of light. In fact, only a fraction of a percent lower than light itself. Then they're flung around the Large Hadron Collider where they meet in various points around the ring. But like I mentioned, one experiment in particular, the ATLAS experiment, takes these snapshots of the collision every time they occur. And so this is the essence of what we're trying to do, is really to take a picture of what's occurring in the collision of these two protons and hopefully try to understand exactly what makes up the fabric of nature itself. So this is all going to go into much more detail, but I wanted you to get a context for the situation that we're actually dealing with. So here again is the ring of the Large Hadron Collider, 17 miles around. And to give you a feeling for the actual size, you have here the Geneva airport, which is just a tiny section on one side of the ring. You can see in the background the Alps of both Switzerland and France. In fact, the border of Switzerland and France runs basically right through the ring itself. And in fact, just to prove to you that, that this was in fact safe, my apartment was actually situated almost right next to one of the collision points. But most importantly, it was far away from the competition, which is the experiment that I don't work on the other side of the ring, called CMS. Now, I'm not going to talk much about that. I will tell you, however, a lot about our experiment, and the one on which a lot of SLAC scientists participate in many different ways, and that's called ATLAS. So that actually sits on the side slightly closer to downtown Geneva and much closer to my apartment. And like Michael said, I didn't have much time to sleep, so that was very useful. All right, so ATLAS is really a global endeavor. More than 37 countries from around the world. As was introduced, thousands of scientists from all over the world. You can see actually here a map which is colored representing the various countries that participate in the experiment. And in fact, as you can see in alphabetical order as usual, the United States is really a crucial player. And in fact, SLAC is just one of many laboratories and universities around the country which contributes to the experiment and to CERN in general. And in particular, the CERN relay race, which you can see a small fraction of the SLAC team here was actually, this is just this year's race. We didn't quite beat the Protons around the ring, but we tried. We didn't come in last, that's for sure. You can actually see a picture down in the bottom right. This is one of the buildings that houses a lot of the graduate students night and day. There's a lock and key on the outside door. We're not usually let out, but there are hundreds of people, which obviously only represent a small fraction of the entire collaboration. Okay, so I've told you a little bit about who the people are which go into this and where they're located, but I'd like to step back a little bit and tell you, I think, at least in my opinion, why we're doing some of this. So I just want to give you a sense first of how big the experiment is. So you can see here, this is a very famous photo of the construction of ATLAS. This is right before we moved this central piece into place. I'll actually describe what that piece is in a little while. And I'd like to point out that this gentleman here wearing a hard hat, we're big on safety, is dwarfed in comparison to the experiment as a whole. And as I mentioned, they do put us hard to work. So this is me crawling around in between the magnet system and one of these electronics drawers here, screwing things into place, and it looks like we got all the cables in the right place. But like I said, I'd like to put this in a little bit more global of a perspective. So humankind has really always sought to understand the world in which we live. We've always asked questions, and we haven't always performed experiments. And one thing that we've learned is that we often need these new ways of looking at the world in order to really begin to see it for its true self. I mean, one way of thinking about that is that new perspectives are really often the result of new technology. When we are able to gaze out at the world with a new device, with a new set of glasses, we often see things that either we couldn't see well enough beforehand or that we didn't expect altogether. And that's actually, I think, one of the driving principles behind the science which is going on both at SLAC and at CERN with these large accelerators, because it gives us a tool to try to understand the world by looking at its most minute components. So to put it another way, oftentimes science is really only as good as its tools. I mean, one wonderful example is Aristotle. He was really the father of modern science in multiple fields. In fact, as an undergraduate, I was confused for a little while and studied philosophy, but quickly got back on track. And you know, from physics to zoology, cosmology, just to name a few, Aristotle really played a key role. But honestly, his lack of experimental data and methods, like thermometers, for example, often led him to draw incorrect conclusions. He famously said that women are fundamentally different than men and have a lower body temperature, and that was one of the ways in which he differentiated the species. And in addition, you might know that he was also a huge proponent of the idea that the Earth is the center of the universe. So a lot of the conclusions that he drew, although informative for science and humankind as a whole, were lacking in his ability to test them against the real world phenomena. And that's something that we try to do in experimental physics, is try to use the knowledge that we have and continually beat it against the wall and ask whether it really has everything that we expect it to in order to move further. So a wonderful example of this is Galileo and the telescope. I'm sure people are very familiar with this. The 400th anniversary of the telescope was just recently. And very famously, he was able to look out into the stars finally with this new device. And one of the first things that he did was to look at the moon. And instead of seeing the perfect spheroidal heavenly body that was purported to be there, he instead saw a very rough, very cratered surface, something that he thought, honestly, looked a lot like Earth. And there was no reason to think that this object out in the cosmos was any different than the object on which he was standing. And this was the beginning of a huge revolution. Obviously, it took until Copernicus for this to really take hold, but it revolutionized, along with Newton later on, who made more detailed measurements, revolutionized our perspective of the cosmos and really allowed us to sort of step back and see beyond ourselves. So we've taken this idea to a whole new level. As just an example, you have the Hubble telescope. So this is the same principle, but a new technology, a new application of the Galilean, of the Newtonian telescope. So it's built on age-old principles, but it allows us, for example, by looking deep, deep into the universe, to see essentially backwards in time. So one thing that the Hubble telescope has allowed us and has told us about ourselves is that there are things early in the universe which are different than the universe today. And in fact, you'll see that this comes back when I describe what the science that we're doing at the Large Hadron Collider in terms of describing the universe in which we live and actually where it has come from and perhaps to some extent where it's going. All right, so this is exactly what I was trying to say. The Large Hadron Collider is essentially another type of telescope. But instead of allowing us to see very far away, it allows us to see the smallest constituents of the universe that there are. And it does so by colliding protons. And really, these constituents are sort of the building blocks of the universe that have been around since the Big Bang itself. And so the endeavor that we are embarking upon is to try to understand those components in order to understand the universe in which we live. So I've been talking a lot about this fabric of the universe, about constituents, and sort of inferring the idea of particles. So what do I really mean? Well, we understand over the last 50 years through experimental and huge advances in theoretical physics that there are a set of fundamental building blocks that comprise the universe. A lot of you are, I'm sure, familiar with some of these ideas. Inside the atom that make up essentially everything that we know, the tables and chairs in this room, we have nuclei, and inside there we have the proton. And then inside the proton, you actually have a somewhat more fundamental object called the quark. And to our knowledge today, this is the smallest component of the sort of physical universe that makes up the things that we know, protons and neutrons, your bodies, the air that we breathe, etc. But so far, the tools that we have not allowed us to go any further. Is there something else behind quarks, for example? This is actually very well represented in this picture where, I mean, it's very clear that we go both by understanding the constituents of nature, we hope to understand ourselves. And so one of the primary tasks that we're trying to do at the LHC is to understand the universe by looking at what it's composed of and the pieces that are there, and in turn, in some cases, the pieces that might be missing. So what we know so far is that we have a set of these particles. And so we have something that we call the standard model of particle physics. And so that's basically all it attempts to do, is to break down the universe into just a simple table. You have a table of blocks which you can build the universe with, and we can put them together in various ways. We can make protons, we can make other particles called mesons, we can make all kinds of things that we know from the world around us. Inside the proton, for example, like I mentioned, are quarks. But in fact, there's 6 types of these quarks. All right, I can deal with 6. That's a fairly good number. But then in addition to these quarks, there's the electron. This is what enables your iPod to play your music and the lights in this room to shine. There are brothers and sisters of the electron called the muon and the tau. Together, these are all called leptons, along with their cousins, the neutrino. Now, you may have even heard about the neutrino. It's a very, very lightweight particle which essentially passes through much of anything. But what's important is that there are these various classes of particles which we know exist. Experiments here at SLAC, at other laboratories around the United States, have proven the existence of these particles beyond the shadow of a doubt. But the question really is this the entire picture that we can construct of the universe? In addition, you have the force-carrying particles, a Z boson. So actually, keep that one in mind. That's something that I'll talk about in the results that we have from the Large Hadron Collider. The W boson, these are very similar. They're related to the weak force in physics. You have a photon, which you're all very familiar with. You wouldn't be able to see me without it. And particle like the gluon, or perhaps the graviton, which might be the force carrier for gravity. But then underlying the idea of these massive particles is something called the Higgs boson. So this is something that you also might have heard about. It's related to the idea of mass itself. And so I'd just like to prime a question to you. Why do the particles of light shining to us from the ceiling not have any mass? We know that. We can test it. They go to the speed of light. While other particles actually do have mass. What's the difference? We have a supposition as to what the fundamental difference between those particles is, but we need to test that. We're scientists. We need to ask the questions that will prove that this is the right way to look at the world. So what is the Higgs boson? Well, you could imagine a crowded room, a cocktail party, for example. I'd just like to surmise that the Higgs particles are like the crowd at a very popular cocktail party. Now imagine a very interesting guest walks in the room, Professor Einstein, for example. As he tries to walk across the room, people want to talk to him. People want to ask him questions. It becomes more difficult for him to move across the room quickly. He has to slow down. He gains some inertia, if you can think of it that way. And so in a sense, these Higgs particles, this Higgs field which is permeating this cocktail party, is slowing down, is giving this professor, this particle, if you will, mass. So the answer to the question is that massive particles are kind of like popular party guests. As they move through this sea of the Higgs boson field, of the Higgs particles themselves, it endows mass through its interaction with these particles. So this is an idea, and we're trying to test this. That's what experimental science is all about. And so the Higgs boson will come back in a little bit. Now, we also know from looking out into the stars and looking at various objects in the galaxies and in the cosmos that there are pieces missing from this puzzle. This table that I showed you is not complete. It's not wrong, but it doesn't tell you the whole story. This pie chart is actually a talk in and of itself, but I would like to point out that the sliver here, this 0.4% of the universe, is really the entirety of the stars and planets and people that we can see when we look out into the skies. There's an entire 99%, except for gas, so there's an entire 96% of the universe which we're not sure what it is. In fact, this sliver here that I've outlined, this 23%, is a very mysterious form of matter called dark matter, which is really the boring physicist way of saying, I don't know what the heck is going on. So what you have in this bottom right picture is something called the bullet cluster. In fact, this is an experimental observation in which SLAC and the Kavli Institute here was crucial in understanding. I'm going to try to explain it to you very quickly, but hopefully understandably. But this is an extremely deep subject in and of itself. In red here, this is false color, are actually the gas, the hot gas imaged from essentially telescopes looking out into the sky of two galaxies that have collided and moved through each other. So this happens all the time. This is nothing to be cried over. Galaxies collide. It's a cosmic car accident, if you will. But in fact, because stars and gases are relatively fluid, they tend to sort of pass through each other with a little bit of friction. And so that's what you see in the red. You see that the gases and the stars are sort of left behind. As they pass through each other, you see almost like a Mach jet passing through the sky creates a sonic boom, and you see the sort of shock wave out in front. You can see that almost clearly on the right side here. But there's another component. There's a whole other piece to these galaxies which you can't see with just a simple telescope. You actually need to use a whole other set of tools to look at this. And when you do so, you see that there's a whole part of the galaxy, in fact, more mass than is contained, as I showed you before, as I showed you in the pie chart, more mass than is contained in the gases themselves has just passed right through. It's not affected. There's no shock front. It's out in front. It's winning the race, if you will. And so this is exactly the stuff that we call dark matter. We don't know what it is, but we know that it's there. You can see it through its interaction via gravity. All right, so we've put this together. We have questions. We want answers. Could there be more to the universe than we see? Could there be more than just our 4 dimensions of space and time? We live in 3 dimensions of space and 1 of time. Could there be another dimension of space? Could gravity be leaking away, and that's why we think we see these weird gravitational effects? Could there be an entire mirror universe of undiscovered particles? Here you have a quark. Here maybe you have an electron. Here you maybe have a tau neutrino. Could there be an entirely other mirror universe that has a sort of analogous particle for every particle in the table I showed you? We don't know. If they're massive enough, they could have sort of hidden. They could be sort of hidden in the fabric of the universe without having been detected in the experiments that we've conducted so far. So we have questions. We want answers. And that's really where the accelerator physics and the Large Hadron Collider come into play. So how does an accelerator show us what these particles are? I think that's the natural question to ask at this point. Well, Einstein gave us a wonderful tool, and that's E equals mc squared. It's a very simple equation, but it's got a very powerful meaning. And it means that on the one hand, you can take energy, that's the E, and turn it into, if you've got the right conditions, matter on the other side. That is, you can sort of trade the energy of motion, that is the energy that you put into a particle by accelerating it, for the mass energy of other particles. All right, so what does that mean? Well, that means that when you collide 2 protons, remember I showed you that we've accelerated them through these boosters, we've got them going nearly the speed of light, and then suddenly we smack them into each other. What can happen is that the energy that you've put in can turn into new particles coming out. So here is actually a set of particles, which I'm going to describe in detail later, called the top quark. So in fact, this is a very interesting particle because it's extremely heavy. Whereas the proton is just a very light particle in terms of the table that I showed you before, the top quark is as heavy as nearly 200 of these protons. And it's just a single particle. Why is it so massive? It's a very interesting question, and we're already beginning to study these things in great detail. So okay, how do we do this? How do we exchange this mass energy? Well, you might have guessed it. It's the title of the talk. We smash protons together. We get protons, or lead ions, as you'll see later, going really, really fast, and then smash them into each other. And so this was very exciting. I mean, this has been done at other places. This has been done at the Tevatron as well, protons, I mean. And you know, perhaps, that SLAC is one of the largest linear accelerators in the world. And so this is a new energy regime in which we attempt to do this at much higher energies. And so the first time we tried to do this, we were obviously very excited. You can see that this is nearly a year ago today. In fact, just a few days more. Excuse me. And you can see the control room. So we have a control room outside above the surface of the accelerator in Geneva. It was packed that day, as you can imagine. Even Google was excited. They changed their famous logo for the day into what you see at the bottom right here. It's not an accurate representation of what the accelerator looks like, but it's close enough. It got the message across, I think. And there really wasn't anything being sucked in, I promise. All right, so the actual machine itself came online in really record time. You can see what I showed you before was just at 8 o'clock, and this is a beam screen monitor of just a few minutes before, and they were able to send these protons all the way around this 17-mile ring, almost without a hitch. And this all went off extremely well. And I'd like to show you what it looks like when these 2 beams are brought together and the protons collide. So I'd like to point out the distance scale here is just millimeters. And as soon as the accelerator operators bring these proton beams into collision, you can imagine them, it's like firing two rifles at each other. You have to be extremely precise, and you have to know exactly what you're doing. So it's going to play again. I just want you to note that this is fractions of an inch here. And so they've steered these energetic beams of protons into one another, and then suddenly what this graph is measuring is stuff coming out of this interaction point. We've got this camera, this giant detector, continuously looking at this one point in space, and suddenly we start to see an extremely large amount of activity, coming out of this interaction. And so this is the sign that protons are colliding and that the physics that we're trying to do has started. So the control room quickly became a lot less fun after that. You can see here a picture of various SLAC graduate students seated in the control room making sure things were okay, while the senior scientists were back in their offices looking at the interesting data. But everything was happening very fast. In fact, this is the control room you saw just a second ago, and on this side you have huge screens and monitors which show you exactly what's going on inside the interaction point, and that's what I'm going to show you. I'm going to describe to you exactly what we see when these protons collide with each other. So I'd like to play this again because I want to highlight the last part of this little animation. So you've already seen the protons start to be accelerated in what we call these booster accelerators and this SPS accelerator before they get dumped into the Large Hadron Collider to really get up to the energy and really the speed that we want. But it's the last part of this animation which is the most informative at this point, because it shows you what we're trying to do. As the protons come in, now that I've told you that their energy of motion can be translated into mass energy, what this picture represents is the massive particles coming out of that interaction point. And we take a snapshot. In fact, this is a simulated image, but I'll show you real images in just a second. And these are particles. These are charged, in fact, protons in some cases, electrons coming out, and we measure their energy and their position in this cylindrical sort of onion-like camera. And that's what we do millions of times a second. So this is the detector. This is the Atlas detector itself. It's 145 feet long and 85 feet tall, bigger than this building, certainly bigger than a lot of buildings on the SLAC campus. And you can see that it's made of a sort of onion-like design. We have various cameras effectively in 3 dimensions, taking pictures in different ways of what's going on at that collision point. For example, if you stood on the detector, which I don't advise, and if you do, wear a safety harness, you can see the vast difference between the size of a person and the size of the detector itself. There's lots of different pieces to the detector that help to measure different things. There are magnets here and here. There's an inner detector system which measures the position, and other systems which I'll describe in a second. But the point is that we have to build such a large machine because the energy going into the collisions is so big that we need enough space to measure what comes out. So here's a snapshot sort of looking down the barrel of the gun, so to speak, when we had it just all cabled up. Here's the centermost piece. In fact, this is exactly where the protons collide. And then you have various pieces in larger and larger radii coming out. Here you see a gentleman standing next to the center. And if you can imagine taking a slice of this detector, like a pizza slice, just from the end-on perspective, then you would see in cartoon form this picture. And so this is actually what the detector is comprised of as you move out from that interaction region. So these are the sort of 3-dimensional, many megapixel cameras, if you want to think of it that way, which allow us to take these snapshots. And what they can do is, for example, this innermost piece, which itself is composed of 3 other pieces, helps us to measure the position of particles coming out. You can imagine that if you want to find out whether it was a proton or an electron, you need to first figure out where the heck it was. And so that's one of the first things that we do is these particles come out from the interaction point. So you can see here that a photon wouldn't even leave a track in this because it's not charged. In fact, these detectors measure charged particles like electrons. But then we have a set of detectors which measures the energy, of the particles. In fact, you can also measure a little bit of the position. They're not as precise as the detectors devoted to measuring position, but they do give you another piece of information, and that's how fast, effectively, depending on the mass, the particle was when it came out of the interaction region. So you can imagine that if you have a very interesting event, you might get something shooting out of the collision point, whereas a lot of stuff sort of just passes through and isn't very interesting, and we have to throw it away. And we do that by measuring the energy and saying, that wasn't very high energy. We don't have enough USB disks to save this, so we're going to throw it away. At the outermost part of the detector, we have something that tries to sort of catch the particles which make it through the rest. For example, the muons. In fact, it's devoted to measuring muons. And it's called the muon spectrometer because it again measures position and momentum, in fact. So now I'd actually like to show you the actual events that we see in these collisions and what we're learning from them. So you'll see a couple of these. This is our sort of quintessential event display. So this is just a single proton-proton collision and the particles which have come out of that interaction region and the tracks and the traces that they've left in our detector. So let's dissect this image from our megapixel camera. You have, as I mentioned, at the innermost region, you have a position measurement device. And so we get what we call tracks. And here it's devoted to measuring charged particles like electrons. You know the concept of static electricity and rubbing two things together and positive and negative charge. And it's exactly those same principles which allow us to measure the position of particles as they move through the detector. But then I mentioned the muon spectrometer, and so just outside of the detector, in this particular event, there was a particle that made it all the way out and left traces of its energy in these detectors. And so we've signaled the presence of a muon in that case. And then lastly, you can see these clusters of energy here and here, for example, which are also in this two-dimensional sort of unfolded view of the detector, which represents something that we call a jet. So you can actually see this by eye. If you just take a careful look, your eye kind of picks out a sort of cone-like structure. It's sort of a spray of particles coming out of the interaction region. So I'll describe what that is in more detail in a second. But now we have sort of a general way of looking at these events. You sort of know the components that are at play here, so we can start to do some physics. So in fact, I told you to remember the Z boson, right? So one of the things that we know the Z boson does is to decay to two muons. So remember, there's this system at the outside of the Atlas detector which is devoted to measuring muons. And in fact, in this event, that's exactly what we see. So we expect the Z to decay to two muons. It doesn't last very long. It's very heavy, but the muons last a lot longer, so we can measure those. And so that's exactly what happened. It's cut off here, but you can see in this bottom picture, which is sort of a slice on the edge of the detector, you can see that these muons came out of the interaction point and left traces in the muon detector here and here. And there were also several jets in this event, which I'll come back to in a second. And so I'd like to actually animate an event like this to show you the whole sequence of events from start to finish. So here we start in the Large Hadron Collider Accelerator, and we go around. In fact, you just saw we went under the French and Swiss border. Dip down into the accelerator itself, where it's actually the quarks inside of the proton. Now, this is a real event. This actually happened. These come into the detector, and then as soon as they enter and collide, you see exactly what I told you would happen. You get a spray of particles coming out of the interaction region. You can measure their position, their energy with the outer detectors, and the presence of a muon. But then you can zoom in, and we can put the pieces back together. We know what we measured, and based on their properties, we can figure out what went into it. So here we see that there was a Z boson, which in this case, instead of decaying to two muons, remember I told you muons are just the essentially brother or sister of the electron. In this case, the Z boson decided to decay to two electrons. And so we've measured the energy of those particles in the colorimeters. We've measured the position of those particles in the tracking detector. And we've put the pieces back together, and we've inferred the existence of the Z boson in a single proton-proton collision. So this is exciting, at least for some of us. But what this allows us to do is it allows us to make detailed measurements of the properties of particles in many different ways, not just the Z boson. The Z boson is just a very good example because it leaves very nice signatures in the detector. But you can make a graph of the properties, the kinematics of these particles coming out. I told you we measure the energy of the electron, right? I told you we measure the momentum of the muons. Well, we can put that information back together and we can make this graph, where suddenly, at certain locations, when you look for muons, you see a peak for the Z boson, and what this peak corresponds to, what's on the x-axis here, is the mass. And so what we've done is we've actually measured the mass of the Z boson by looking at the energy or the momentum of the particles it decays to, because they essentially carry information about what the parent particle was. You can do the same thing, for example, in the event I just showed you, with electrons. And so again, at the same position, you see the mass of the Z boson. And so these are detailed, delicate measurements that can be done across a very large range of energies. And you actually see many other particles in this spectrum. In particular, one I'll mention later is, for example, the J psi, which is a particle which was at least co-discovered right here at SLAC. And so all this entire spectrum is kind of like picking apart exactly what has gone in when these protons collided because of what came out. And so these measurements show us that there are massive particles which are being created when the protons collide. Now, this is kind of old news. The Z boson was discovered in 1983. But the point is that we're using this information to then look for new particles. And that's exactly where we're going next. But I need to explain to you what these jets actually were. And so, for example, remember that the proton is made up of these quarks. But the quarks themselves are held together. Protons, the table, and the desks that you're sitting in front of aren't just flying apart spontaneously. They're held together. The protons aren't simply decaying. Now, the quarks interact via a force called the strong force. But you can think of it, and this isn't necessarily the best explanation, but it's a useful one, of these being held together by springs. So you know that when you compress a spring, it gets more and more difficult as you compress it more and more. You're putting energy into that spring. And if you pull it apart, hopefully it doesn't break in your hands. Depending on how big it is, that might hurt. Your car bounces up and down when you drive down the street, depending on what kind of suspension system you have. My old car certainly does. And what you see is that the spring-like force essentially prevents the quarks from flying apart. But now we're colliding them. We're colliding them at the speed of light, and the energy that you're putting in is essentially breaking those springs apart. And again, just like Einstein told us, that energy can be used to create new particles when those springs break. And so this is what ends up happening. You break these springs apart, but new particles are created in the process. So you get this regeneration, this spray of particles coming out, just like you saw by eye. You saw this cone-like distribution of particles in the jet, and that's exactly what we're talking about. So here again is another image. In fact, this is the one on the poster for the talk today. And you can see just what I was talking about. You have a spray of particles coming out. You have measurements in the calorimeter. And in fact, this corresponds nearly exactly with what we expect from the picture on the right side here. So these jets of particles tell us, again, about the fact that there were quarks in the proton-proton collision. Now, what we can do, this is another picture of two jets, is we can look for a heavy particle, just like we did with muons and electrons. We can say, well, I know that there are pieces of the standard model that are missing. I showed you that. You know, we think that there are particles there that we don't know quite a lot about. And so can we sense the existence of these new particles? Or, for example, can we see if there's pieces inside the quarks themselves? And so if you look at events like this, where you have a jet on one side and a jet on the other side, this might be because of the decay of a heavy particle. Right? I told you that Z bosons decay into electrons and muons. Why can't a new particle potentially decay into quarks? So this is one of the first new measurements that we've done, and in fact, this set one of the world's best limits on the presence of these new particles already. This has happened in just the last couple of months. So by making, remember I showed you that spectrum of mass from the Z boson, right? Or other particles as well, but related to the electron decays and the muon decays. You can do the same thing for the quarks. So you see here a graph of the reconstructed mass of these quarks that have come out and formed jets. But then you look inside, you don't really see any bumps. From the Z boson, we saw a very clear peak in the spectrum. From the J psi, we saw a very clear peak. Why don't we see any peaks here? Well, if there is a new particle, then we must not be sensitive to it yet. And so what this graph tells you is it says that if there's anything there, it's much harder to find than what we've looked at just in the first few weeks of the experiment. So we're still working on this, but it tells you that we don't see a bump like this, and therefore, if there's a new particle, it has to have a mass much higher, much further off the end of this spectrum than we've collected in just a few weeks. All right, so this is actually one of the first new results that we've established. This moves beyond, this pushes the envelope further and allows us to make statements about the world in which we live. But we can put all of this information together. I've told you about muons, I've told you about electrons, I've told you about jets, how we've used jets to search for new particles. I've also told you about what we call the top quark. And this particle is very interesting in and of itself. Now this event, I'm going to lead you through and then tell you what's interesting about it. So try to follow along. So first we have a muon here. We've measured this in the muon system. It's very clear. You can see it in this display on the right side here. So we've seen this particle. We know what it is. Good. But we also have an electron in this event. We have an electron whose energy and position we've measured on this side. We also have a couple of jets. So we know how to use jets. We know how to put them together with the other information in the event in order to ask questions about what happened. And that's exactly what we've done in this case. And in fact, this combination of particles and some measurements about their energy and momentum in particular tell us that we've seen exactly what we expected from a top quark decay. I showed you at the very beginning these two top quarks coming out of the proton-proton collision, and that's shown here and here. But just from theoretical principles, Michael and his colleagues will show us that on one side we expect a jet, on the other side we expect a second jet. I just showed you that we've seen two jets in this event. We also expect a muon on one side and an electron on the other. When I say side, I'm just referring to the two different top quarks which we produce. So this theoretical picture has been shown experimentally in a very complicated situation. We've used all the pieces of the detector to prove that this has actually happened. So this is the direction that we're going. We can use this information. So we've now measured masses and cross-sections, that is, rates at which these things happen. And we can put this all together to search for new physics. I'd like to point out one last thing, in particular because it's been in the news recently, and that's that we have the ability to collide lead ions together. So instead of just colliding individual protons, you can essentially collide bags of protons in the form of an entire nucleus. All right? So instead of a single proton, you have hundreds in this case. Right? So here we have two lead atoms which have been stripped of their electrons, so just the ion, the nucleus itself, and it's collided, and you can see the debris of particles left behind. This is obviously a simulation. But what the idea here is that I've told you about the sort of nature of quarks, right? They want to stay together. They have these spring-like forces holding them inside the proton. But at the beginning of the universe, at the very first seconds of the universe, it didn't have to be that way. It was so hot and so dense that it's possible that these things were free individual particles. Now, this brings us full circle to the idea that the LHC is allowing us to look back at the earliest times and tell us about the earliest stages of the universe when, instead of being locked together into protons and neutrons and other mesons by the strong force, they could have been set free. So we can try to recreate this sort of primordial soup by colliding the lead ions instead of just individual protons. And we've done exactly that, and I'd like to show you an actual collision. This is quite dramatic if you compare to what you just saw a second ago. So again, you have, in this case, the lead ions coming together, and now they're going to collide in the center of Atlas, but instead of just a few tracks, you see thousands. So you can remember the picture that you saw a second ago where you just had a few pieces of the detector lit up. But in this case, you have the entire colorimeter, that is the energy measurement device, full of energy. You have the position measurement. I'm going to play it one more time. You have the position measurement device or the tracking system completely full of tracks. And what this has allowed us to do is it allows us to make detailed measurements of exactly what happened when these lead ions collided. And it, in a way, and in fact results that have kept me awake for the last week, show us that this is in fact telling us new things about the nature of the quark-gluon plasma, or this primordial soup, which was potentially present at the very earliest stages of the universe. So here you can see just a head-on view like the one I've been showing you of the quark soup itself. You can see that it is completely full. You have energy measurements all around the outside of the detector. And in fact, you can see that the energy is completely distributed throughout the calorimeter system. And this actually tells us, once you look inside this in more detail, that there are things going on there which tell us how this quark-gluon plasma, this soup, actually operates. And so this is actually potentially one of the more interesting discoveries and measurements that we've made in recent times at the LHC. I'd just like to point out that this particular event occurred just a couple weeks ago. And in fact, just over the last week or two, we've made some very interesting measurements related to this, which, if you're curious, I can show you a slide at the end. So I've brought you through a long set of interesting measurements that we've made, but I haven't really told you about the giants whose shoulders that we're standing on, to some effect. And so here you see a timeline where over the last half century, we've really been putting together this picture that I've tried to describe to you. We've discovered particles in bubble chambers, in cloud chambers. We've discovered several particles here at SLAC. We've discovered particles at Fermilab, at CERN, and other places around the world. And this is what has given us the confidence to make the measurements and interpret the data that we've seen. But in fact, in just a few months, we've effectively repeated what has gone on over the last half century in order to reassure ourselves that we know what's going on and that we understand the picture that we've painted over the last half century. Because in order to move beyond that, you need to have a firm foundation on where you stand. And so that's exactly what we've been doing. We call it sort of rediscovering the standard model, sort of rediscovering the universe that we know in order to establish signatures of things that we don't know. And so there's a long road ahead of us. We've taken baby steps so far, and we have a lot of big steps to take in the years to come. The end of the physics run this year and next after the holidays will hopefully tell us a lot of new things when we're able to analyze the data that we've collected so far. But we have a whole host of theories that we'd like to test and ask questions about. I've told you about the supersymmetry, this mirror universe that might exist. We're already starting to probe the potential existence of these mirror particles. I've told you about the Higgs particle. This is a bit more difficult to discover, and we expect that over the next few years, as we collect data and understand what we've measured so far, we will become sensitive to new things like the Higgs extra dimensions. I described to you that this is one hypothesis as to what might be the reason for gravity acting the way it does. And so this is really decades of understanding and discoveries about the universe in which we live that lie ahead of us. So just to summarize, I've told you a lot of things. I've told you that we've essentially mapped out the world in which we live, but we know that there are pieces of that picture which don't quite fit. We know that there are missing pieces in this standard model of particle physics, and we are already trying to understand that today. The instruments that we've built allow us the opportunity to test this picture, to look beyond that which we know, and honestly, this is taking place at the highest man-made energies ever created. We've already rediscovered how well our standard picture works, and as I mentioned with this picture of the jets, we're already even moving beyond it. We're taking steps beyond that which we've already been able to establish and looking further. We're able to validate some of the most complicated physics we know of to date. This top quark picture, which I showed you, took potentially decades, depending on where you start counting, to truly understand and piece together all of its components to make these measurements, and we've already been doing them in just the first few months. So for the next decade, the LHC is really expected to continue to deliver science at the energy frontier, providing both precision tests of what we already know, and I've showed you that, we're already conducting them, and hopefully putting together and discovering the pieces of the universe which we think we know are missing. Thank you.
So, David, thank you very much. We do have time for questions. Now, please wait
You
for...
seem too eager.
Please wait. We have two guys, David and Wells, here with microphones. Sorry, Dan. I'm sorry. Dan and Wells with microphones. So when I call on you, you'll get the microphone and wait for that before you ask your question. So let's start with this fellow here, and you're next.
Just two questions. So what's the highest energy level the LHCs hope to attain, and why does the Higgs not interact with photons, but it does with neutrinos?
But it does with?
Neutrinos.
Okay. So that's a very deep question.
Actually, if you'd repeat the question.
Yes. So the question was, what is the highest energy that the Large Hadron Collider hopes to attain? And the second question I'll repeat in a second. So the current energy that we're running at is what we call 7 TeV. So an electron volt is the energy that an electron gets when you accelerate it through 1 volt of potential difference. If you have a battery of 1 volt and you let the electron go from one side of the battery to the other, it will have 1 electron volt. All right? We collide the protons at 7 trillion electron volts, 7 tera electron volts, or TeV. Now, this is actually half of the design energy that the LHC is meant to achieve. That's 14 TeV. The reason for not doing this is because of certain instrumental effects, which, if somebody else asks, I can show you a few slides on. So it's basically, at this point, a safety measure. The magnets which I showed you, that blue tube that the protons accelerate around, is actually kept at almost absolute zero. It's colder than outer space. And so what happens is when you accelerate the protons around, there's a small chance that one of these protons goes into the magnet instead of into the collision point. It's a small chance, but it's there. But what that means is it could heat it up a little bit. And when you heat up something which is kept at absolute zero and which has lots of superfluid liquid helium inside of it, there's the potential for doing some damage. And so as we understand, and this actually goes back to understanding our tools and methods. As we understand more about how the machine works, we will raise that energy. In fact, when the machine turns back on after the winter holidays, it's expected to raise the collision energy from 7 TeV to 8 TeV, for example. So the second question was, why does the Higgs boson interact with neutrinos and not with photons? And the reason is because of the demarcation, essentially, of forces. There's the sort of electroweak sector and other sectors, and the photon simply by construction doesn't couple to the Higgs field. Okay. In fact, I would defer to theorists for why this happens at a more fundamental level. But I think this is beyond maybe the discussion here. We could talk about it afterwards. But there is a difference between what the particles are that are neutrinos, in fact, other leptons, and the force-carrying particles, the Z boson, for example, and the photon itself. They're different sets of particles, and they simply don't essentially talk to each other.
Sir, up there.
If there are 6 types of quarks, and your diagram showed that there are 3 of them comprising a proton, what do the other ones do, or is it always the same ones that are the proton? And if I may go on then, if the top quark weighs 200 times as much as a proton, then clearly it's not one of the ones that's in there.
Nope.
And is it only then created from the energy of the collision and instantaneously decays, and does it exist in any other form at any other time, anywhere?
That is a wonderful question. In fact, I have answers to various components of it, and I will repeat the question itself. So the question is essentially, if I have this table of 6 quarks, why do you only see, in fact, 2 of them in the proton? Only the up and the down quark are present in the proton naturally, so to speak. Okay, so I'd like to go back to this plot here. So there are 6 different types of quarks. And so the question goes on to ask, then how does this differentiate? How do the quarks in the proton differentiate from other quarks? For example, the top quark, which is so much heavier. So there's multiple questions inside there. So the first point is that I mentioned a few times, on my apologies without explaining very well, particles called mesons, for example. These are different cousins of protons and neutrons, which are baryons. These are just categories, and physicists like to pretend that we're ancient Greeks and give them strange names. But the reason that you only have the 2 types of quarks in the proton is that they're the lightest ones. So the up and the down quark are essentially the lightest quarks out of that family. And because of E equals mc squared, if you have something that's a little bit heavier, you can often you can decay it into lighter particles, okay? And so what happens is that the stable particles, protons, are made of the most stable quarks, the up and the down quark, but the other quarks can form particles like the kaon, can form particles like the omega, can form particles like the xi. So this, or cascade, depending on how you like to talk. So these do form other particles. In fact, you have a particle studied and discovered here at SLAC called the JAPE psi, which is made out of the charm quark. Okay? And so the charm quark is one of the, I can just go back to the table for people who are, who would like to visualize this. There we go. So here you have the charm quark. This is in the second group of quarks. So they typically group up and down in this table. So up and down quarks often go together, charm and strange quarks often go together, and top and bottom quarks often go together. And that brings us to the answer to the question of the top quark. Why is it so different? That is a fundamental open question in science. Why is the top quark so many hundreds of times heavier than the other quarks? It's something that even has a name. It's so famous that we don't understand. It's called the hierarchy problem. Why is there this strange ladder of masses inside this table? And in fact, in the other tables as well. We don't know the answer to that question. However, there was a part that we do know the answer to, and is what does the top quark do? Since it's so heavy, you, I think, hinted at the answer, which is that it decays almost instantaneously. But remember I told you that the table here often is grouped together up and down. The top quark will decay to the bottom quark. They're in the same so-called doublet. Disregard that comment. Anyway, and so what happens is it decays into the bottom quark and a W boson. So you'll get these particles coming out. So if I go back to the plot that oh no. If I go back to the plot that I showed you. There. In fact, what this shows you is precisely the answer to your question. The top quark has decayed into this B quark. The B quark, because it's a quark, forms these jets of particles. I told you about those guys. That's here. But then it also, the cousin that it the boson that it decays to is called the W boson. And then that, in turn, because it is so heavy, decays to other particles called the muon and the neutrino. Does that answer most of your question?
Where?
What do you mean where? Instantaneously.
But in stars because of collision?
So yes, part of your question was how do we produce the top quark?
Or where does nature produce it?
Nature can produce it in highly energetic collisions. So in fact, all the time, there are cosmic rays from stars and from particles that are accelerated out in the universe that collide with the upper atmosphere. So it can be produced there. This is more related to the question of black holes. But it can be produced up in the upper atmosphere. But again, this is going to decay so fast that it's going to turn into a shower of other particles long before it reaches the surface of the Earth. So on the Earth, in our everyday lives, the only place that this particle is ever produced is in a particle accelerator.
It's a real mystery why we have all these species that seem to not live anywhere in the universe and decay very rapidly. Stars, ordinary stars, don't have enough energy in them to produce a top quark. Let's see. Over there, please.
Get off the black
My
hole
question is about the detectors.
Yes.
Are these bubble chambers or Cherenkov radiation detector, or what's the nature of these detectors you have?
Great question. I actually planned for that one. Okay, so this is the 87 megapixel camera at the heart of the Atlas detector. This is actually a piece of this detector has been an integral part of the contribution that SLAC has made to the Atlas experiment as a whole. In fact, we've worked on the innermost part. SLAC has a lot of expertise in designing what we call vertex detectors. I've told you that we have to recreate and measure the positions of these particles at the very heart of the collision, and that's exactly what this so-called pixel detector or silicon pixel detector does. This is just like, well, not just like, related to your digital camera. You remember we all, I don't know, Black Friday, anybody go shopping? Anybody buy a digital camera? Woo! Yes. Probably bought a 14 megapixel camera, 15 megapixel camera. What that number means is how many millions of pixels are on the chip, which allow you to image whatever light is coming into the focal plane from the lens of the camera. But what we do here is we set up those pixels in a sort of soda can-like cylinder, and we give them various layers. So in fact, here's the pixel detector, and instead of your camera, which has just one layer, and that's why you get a two-dimensional picture, we have 3 layers, and that's why we get a 3-dimensional picture. We can measure how far out it's gone, as well as how long, what position along the detector it's been created. And so, sorry, I lost the gentleman who asked the question. Ah, there. Yes. Yes, so this in particular is solid state. And then as you move outside of that, there's another silicon or sort of solid state, if you will, detector, which is made of strips. So instead of individual little sort of squares or rectangles that are each read out individually, here you have just strips of digital camera-like material. And then outside of that, we have a drift chamber. And so this is along the lines of the cloud chamber that you were talking about. But it's different in that we measure the passage of particles through the gas, and then we measure the ionization or the electrons. Right. So we don't have any. Excuse me. We don't have any Cherenkov detectors in the Atlas detector. Other experiments other experiments besides CMS that are more dedicated to specific measurements do have Cherenkov detectors. That's not true. We have a detector at the very end of Atlas, which is not used in any of the measurements I've shown you, except to detect that a proton has gone by. And that does use Cherenkov radiation.
You're just detecting the electrons that are knocked out of the silicon by the particles coming out?
Yes, in most cases, yes. So we measure things via ionization primarily, and scintillation light in some cases as you move further out. But yes, most of it's based on electronic signals. So here we have the Atlas sort of thermometer system, or the calorimeter. Now this has 2 main systems. The innermost system here is the electromagnetic calorimeter. That is primarily dedicated to measuring photons and electrons, or things which interact and leave electromagnetic radiation. But then in addition, there are, if you had a proton which is passing through here, instead of just a photon or electron, it's also going to interact via the strong interaction, or sort of nuclear interactions. And so we have another component outside of that called the hadronic calorimeter. Now the liquid argon calorimeter, this is why I mentioned the ionization and the scintillation light, because it has liquid argon. So it's argon cooled down to a temperature at which point it becomes a liquid. And as charged particles pass through it, it leaves ionization. It knocks electrons out of the atoms of the liquid argon in the liquid, and then we measure that on electrodes. And then the tile calorimeter is called a tile because it's got pieces of plastic tiles inside You can almost imagine that each of these little slits is a piece of plastic, and as particles pass through the plastic, it creates light. And then we measure the light using a light detector, which are actually represented by these little green dots up at the top here. And so we put all of the pieces together, both ionization, scintillation light, etc., to measure the energy in that particular case.
This man here, please. Yes. No.
Is this an event-based experiment, or is this a continuous, reproducible, predictable experiment? And what role does probability play in potentially, sometimes it'll decay one way, and another time it'll decay another way?
That's the answer.
And that's the answer?
Yes.
So then how do you know specifically what the nature of matter is, except that it's a probability? It's not an actual existence of a particle.
Well, okay, I mean, that's a little bit of a philosophical question.
I can only ask philosophical ones, not knowing enough.
It's a good thing I studied philosophy. So, I'd like to go back to the mass distribution plot that I showed you. So the way that we construct this plot is not from a single event. That's why when and maybe I didn't quite say it right, but that's why when some of these events were shown, there was the word candidate on it. There was the word, top quark candidate event. Because on an event-by-event basis, you can be fairly certain that that's what happened. But there's the possibility that you made a mistake. There's the possibility that there was even something there that you didn't quite understand yet. But the point is that when you collect a whole series of such events, you can make plots like this where this is unmistakable, where you have a peak at a very particular energy. And in fact, the reason that this isn't just a single point coming way up, it has some spread, right? We don't always measure the Z boson with exactly 91.6 GeV. We have some error on that measurement. Because we measure things with a calorimeter for which the electron signal coming out maybe always wasn't perfect. Because when we measure the position of the muons in the tracking detector, maybe it wasn't always perfect. And so yes, we are a probabilistic beast in terms of how we understand the world. But I would like to claim that the world is probabilistic.
Yeah, I'd just like to comment that we are here deeply in the world of quantum mechanics. And Einstein was wrong. God does play dice. And you just have to deal with it. Okay, the hour is getting late. Let me take two more questions and then we'll break. So
I'll stick around.
Sir, please.
The top quark has a mass of about 173 GeV, and Fermilab has already eliminated that as too large a mass for the Higgs.
Yes.
It has to be less than 160 and more than about 110 GeV. That would mean that Fermilab has actually detected them, but haven't said so. What's your comment on that?
No, that doesn't mean that they've detected them. Remember I showed you this plot where I said that we looked for something and didn't find it? Right here. And so that's setting what you call a limit. And because of certain experimental peculiarities, there's more sensitivity by the Tevatron experiments in that particular mass window. If a Higgs boson had 170 GeV, they would have seen it. But if it has 120 GeV, they might not have. If it has, in fact, there's another piece where if it's above a certain energy, a certain mass, they wouldn't have seen it also. And so it's what's called an exclusion limit. And it doesn't mean that they've seen it. It means specifically that they haven't seen it in a particular place.
Last question. Sir, up there. Yes.
When you sum or attempt to sum the mass energies of the products of the single proton collision, what fraction of the input energy comes out?
That's a very good
or
question.
Or what can you account for?
That's a very good question. Well, wow, there's a lot of pieces to that. So a very small fraction in general. We put in, as I said before, 7 TeV. But oftentimes what we measure is just a few hundred GeV. Now these numbers are 3 orders of magnitude different. GeV is a billion, TeV is a trillion. So what I'm telling you is that we often only see in the interesting particles 5–10% of that energy. And that's because a lot of it, remember, it's the whole proton which has 7 TeV, well, the collision of the two protons is 7 TeV. Each one has 3.5. But it's carried between 3 quarks. So you have to divide that up, first of all, between the quarks. And then all of that momentum, all of that energy isn't always transferred. Okay? Again, partially because it's probabilistic. So the short answer is a few 5-10% for the interesting events and almost nothing for the non-interesting events.
Does anybody speculate that you're missing something? I mean, there's something yet to be discovered?
Absolutely.
Okay.
Otherwise, I'm out of a job.
Okay, well, as you probably see, we could keep David up here talking all day, but I think I'd like to release you folks. However, some of David's colleagues, Bart, Wells, where are you? And Dan will stick around. They'll be wearing these hats. David will stay here. I'll stay around. Any questions you have, we'll talk to you privately. But let's thank David again for a beautiful talk. And we'll see you all in January.